So right now, we have the exact mathematics to basically slingshot a crewed capsule like 400,000 kilometers around the moon, right? And we can drop it into a super precise recovery zone in the Pacific Ocean.
Right, down to the exact mile.
Yeah, but at the exact same time, we literally cannot legally force a commercial company to clean up a piece of orbital debris the size of a coin.
A coin that could, completely vaporize a billion-dollar communication satellite.
Exactly. We are engineering at the absolute edge of the future, but our laws and our physical infrastructure are, well, in a lot of ways, they're stuck in the past.
And that paradox is really the defining challenge of our era. The pace of technological innovation is accelerating so rapidly that the science is just entirely outpacing our capacity to govern it.
Welcome to a custom-tailored deep dive into a stack of sources covering exactly that collision. We're looking at outer space governance, next-generation energy infrastructure, and atomic-level computing.
In massive scope.
It is. And if you're listening to this, you're looking to cut through the daily noise and really grasp the underlying mechanisms driving global policy and scientific advancement. Think of this source material like a vast, uncharted map. Our mission today is to drop pins on the most critical developments and, draw the lines between them.
Because whether we are analyzing the Artemis lunar missions or India's Gaganyaan spaceflight program or even the economics of prototype nuclear reactors, the common thread is clear. Humanity is operating at the absolute limit of our understanding.
Yeah.
The math usually holds up perfectly in a vacuum, but applying that math in the real world reveals these incredibly messy logistical and political realities.
Right. So let's start mapping those realities with the new space race. The Artemis II mission recently broke the distance record for a crewed flight, taking astronauts over 400,170 kilometers from Earth.
Using the massive Space Launch System rocket and the Orion capsule.
Exactly. They completed a lunar flyby, which is the first in over 50 years. But scanning the mission debriefs, the most striking detail wasn't some piece of billion-dollar hardware. The lead scientist, Kelsey Young, specifically noted that the astronauts were using their own eyes to witness meteorite impact flashes on the lunar surface.
Which is amazing.
She called the human eye the best camera that could ever or will ever exist.
And she's not wrong. I mean, digital sensors are extraordinary, but the human eye is still unparalleled at simultaneously interpreting true color, contextualizing peripheral surroundings, and making really rapid photometric observations in dynamic lighting.
It's a powerful reminder of why we send humans, right? Like absorbing all that massive risk and cost rather than just relying on robotic probes.
Absolutely. But, Artemis isn't just about pure scientific observation. It is the leading edge of a profound geopolitical contest, primarily structured between the United States and China.
And the structural differences between those two programs are just massive. The U.S. is heavily leveraging a commercial model. So they're relying on private partners like SpaceX and Blue Origin to build the hardware,
while simultaneously binding an international coalition of, I think, over 50 countries together through the Artemis Accords.
Right, and those accords are highly controversial among international law scholars, aren't they?
Very controversial. On paper, they establish safety norms. But in practice, legal experts point out that the accords create a framework for the U.S. and its partners to establish safety zones on the moon,
which effectively allows them to consolidate control over finite, high-value areas, like the water ice deposits at the lunar South Pole.
Exactly. And that circumvents the spirit of the 1967 Outer Space Treaty, which explicitly forbids national appropriation of celestial bodies.
Right. Now contrast that with China's strategy, which is a highly integrated, state-driven model. They're advancing their Mengzhu spacecraft and Lanyu lunar lander while basically weaving their space infrastructure directly into their Belt and Road Initiative,
locking partner nations into their satellite and data services.
Yeah. And what makes this modern space race so bizarre is that these tangible, multi-billion-dollar engineering feats are actively competing with fabricated realities. The sources discuss this concept of the liar's dividend.
Oh, right. The deepfakes.
Yeah, this phenomenon where the sheer availability of advanced AI tools gives people plausible deniability to claim real events are fake. We saw viral claims that the Artemis II footage was just AI-generated, which perfectly feeds into those old Apollo hoax conspiracies.
Because as our technological achievements become increasingly complex and, removed from everyday human experience, They become prime targets for disinformation.
Totally.
The average person cannot independently verify a lunar orbit, making them incredibly vulnerable to manufactured skepticism.
Okay, so taking humans out of the deep space equation for a second. The physics of simply getting a crew module back to Earth from low Earth orbit is violently unforgiving.
Violently is the right word.
This is the immediate hurdle for India's Gaganyaan human spaceflight program. The uncrewed test flight has faced delays, but the human preparation is intense. ISRO recently ran mission Mitra in Ladakh at an altitude of 3,500 meters.
To simulate the hypoxia, extreme cold, and psychological isolation of spaceflight.
Right, testing how astronauts and ground control make critical decisions under extreme physiological duress.
And simulating that stress is non-negotiable because the re-entry phase is arguably the most dangerous part of the entire mission.
Yeah, let's talk about that.
When the Gaganyaan crew module returns, it hits the Earth's atmosphere at roughly 7,800 meters per second. The module has to shed all of that incredible kinetic energy without, vaporizing the astronauts inside.
Which it does through aerobraking, right?
Yes. It uses the atmospheric drag itself as a giant brake pad, converting that kinetic energy into extreme heat, which is then absorbed and dissipated by the ablative heat shield.
Right. And then the parachutes deploy when the module drops to about 12 kilometers above the ground. But wait, let's pause on the math here.
Sure.
If we possess the computational power to calculate a slingshot trajectory around the moon, why is the final act of parachuting a capsule into the ocean still so mathematically unruly that we have to aim for this massive, elongated, elliptical target zone in the Bay of Bengal?
It fundamentally comes down to the physics of aerodynamic drag. Specifically, there's an inverse square relationship between the terminal speed you want to achieve and the surface area required to achieve it.
Okay, unpack that for me.
You cannot simply deploy standard parachutes to slow a multi-ton capsule down to a gentle, controlled hover. If you want to slow a module from, say, 7 meters per second down to just 1 meter per second, you don't just need a slightly bigger parachute.
You need a massively bigger one.
Exactly. The parachute would have to be roughly 49 times larger.
Wow. A parachute 49 times larger would be the size of a stadium. The weight and volume penalty alone would completely ruin the launch math.
Furthermore, deploying a canopy of that size at high velocities creates a catastrophic tangle risk. Because the capsule is moving at hypersonic speeds upon initial re-entry, even a microscopic fluctuation in atmospheric density.
Or like a tiny variation in wind shear?
Exactly. It gets magnified across the entire descent. The module's kinetic energy is entirely concentrated along its forward flight track, leaving it with virtually zero lateral control.
So they can't just steer it to a bullseye.
No. They calculate an elongated ellipse, accounting for all those atmospheric variables, and the Navy positions recovery ships across that entire zone.
Okay, you mentioned the module having virtually zero lateral control during that descent. That implies the flight path back down to the ocean has to be completely clear of obstacles.
It absolutely does.
So how are we mapping what is actually in our way, both out in deep space and right here in our own orbital backyard?
Well, mapping the deep cosmos requires entirely different mechanisms than tracking local debris. Recently, astronomers from IIT Kanpur made a significant breakthrough in measuring vast cosmic distances using pulsars.
And pulsars are the spinning, hyperdense cores of dead stars, right?
Exactly. They emit beams of radio waves that sweep across space at perfectly precise intervals. They act like cosmic lighthouses.
To appreciate why this is a breakthrough, we really have to look at the traditional parallax method. Parallax is just basic geometry like holding your thumb out and looking at it with alternating eyes. Your thumb seems to shift against the background.
Right, and astronomers do that with stars by measuring their position from opposite sides of Earth's orbit.
But that only works for relatively close objects. Eventually, the distances become so vast that the geometric angles get too microscopic to measure. That is the hard limit of parallax.
And the IIT Kanpur team bypassed that geometric limit by analyzing how the light from those pulsar lighthouses gets distorted on its journey to Earth by the interstellar medium.
Specifically, massive clouds of ionized plasma.
Yes. They use two distinct physical effects. The first is the dispersion measure. As radio waves from the pulsar travel through plasma, the free electrons in that plasma physically slow down the lower frequency waves more than the higher frequency ones.
Oh, so by measuring the exact time delay between the frequencies arriving at the telescope, astronomers can calculate how many electrons the signal passed through.
Precisely, which gives them a rough distance estimate. But plasma clouds in space aren't perfectly smooth. They are turbulent.
Which leads to the second effect, right? Scatter broadening.
Yes. The plasma scatters the radio waves, forcing the light to take multiple slightly different paths to reach Earth. This makes the pulsar signal look temporally smeared, or makes it twinkle.
So by combining that dispersion delay with the calculations of that scattering effect, they can pinpoint the exact location of incredibly distant, complex plasma structures like the Gum Nebula.
Completely shattering the distance limitations of parallax.
It's incredible. We are successfully mapping regions of the universe millions of light years away, yet our immediate low Earth orbit is just devolving into a terrifyingly chaotic environment.
It's a stark contrast.
The Indian Space Situational Assessment Report for 2025 highlights a staggering reality. 315 global space launches placed 4,651 new objects into orbit in a single year.
And this is where we shift from brilliant engineering to a profound failure of global governance. The risk isn't just about two large satellites bumping into each other.
We're talking about Kessler Syndrome.
Exactly. These objects are traveling at roughly 17,000 miles per hour. At that velocity, if a dead satellite collides with a rogue booster stage, it doesn't just break into large chunks.
The kinetic energy basically vaporizes the metal into a shotgun blast of thousands of microshrapnel pieces.
And each of those pieces can then destroy another satellite, creating a cascading chain reaction of destruction.
And the legal frameworks governing this environment are just complete relics. The Outer Space Treaty was drafted in an era when space activity was incredibly rare, slow-moving, and controlled exclusively by a few sovereign nation-states.
While the treaty holds states generally liable for damage, it completely fails to address cumulative harm or environmental stewardship.
Right. There is no legally binding international duty of care standard for orbit. Regulators today are mostly just relying on voluntary promises from private companies regarding what they intend to do with their satellites at the end of their operational lifespan.
Which is severely inadequate.
It is the equivalent of building a busy, high-speed highway where no one is legally required to tow away their broken-down cars, and there are no penalties for leaving debris in the fast lane.
That's a great analogy.
But let me push back here. From a purely practical standpoint, if a piece of debris the size of a coin can destroy a satellite, but our radar systems can't reliably track an object that small until after it has already caused a collision, how could any regulatory body practically enforce a duty of care?
It's a great point. Post-collision enforcement is nearly impossible with current radar limitations. This is exactly why policy experts are shifting the focus entirely toward preventative licensing.
Ah, okay.
As India drafts its upcoming national space legislation, there is a massive push to embed verifiable end-of-life disposal strategies as a strict legal requirement before a launch license is even granted.
So moving away from self-policed guidelines.
Entirely. Operators would be forced to prove they have the physical propellant reserve to deorbit their tech. They might potentially mandate the funding of escrow accounts or massive insurance premiums to internalize the economic cost of a clean orbital environment.
Okay, so we are talking about regulating space debris and imposing strict new legal standards for satellite disposal. But the paradox here is that tracking millions of microshrapnel fragments, processing that petabyte-scale radar data in real time and manufacturing cleaner rockets, that demands exponential leaps in continuous baseload energy.
It absolutely does.
We literally cannot clean up space or scale our data infrastructure without a fundamental upgrade to how we generate power on Earth. Which is why India's recent milestone to the nuclear frontier is so critical.
Yes, the prototype Fast Breeder Reactor, or PFBR, located at Kalpakkam. It has officially achieved criticality, successfully sustaining a controlled nuclear chain reaction.
This represents the realization of the crucial second stage of the three-stage nuclear program, originally conceived by Homi Bhabha in the 1950s.
And understanding that three-stage architecture is vital for grasping India's long-term energy economics.
Right. Stage 1 relies on pressurized heavy water reactors, which consume natural uranium. The problem is, natural uranium is overwhelmingly composed of the U-238 isotope, which does not fission easily.
The reactors only extract energy from the tiny fraction of U-235 present, leaving behind massive stockpiles of depleted uranium.
So the Fast Breeder Reactor is stage 2, designed to solve that exact inefficiency.
Right. It takes that leftover depleted uranium and wraps it around the active reactor core like a blanket. The core bombards that blanket with high-energy or fast neutrons.
And this bombardment physically transmutates the useless U-238 into plutonium-239, an incredibly potent nuclear fuel. The reactor literally breeds more fissile material than it consumes.
Exactly. And this stockpile plutonium is the necessary bridge to stage 3, which will eventually allow India to utilize its massive, globally unmatched reserves of thorium for near-limitless baseload power.
But we have to analyze the engineering realities impartially here. Getting the PFBR to this point has been an incredibly bruising process. The project is 16 years behind its original schedule.
And the capital costs have ballooned beyond 8,181 crore rupees.
A major reason for this friction is the coolant mechanism, right? Unlike stage 1 reactors that use water, the PFBR uses liquid sodium.
Liquid sodium is a phenomenal heat transfer agent. It pulls heat away from the incredibly dense hot core far more efficiently than water, and it does so at normal atmospheric pressure, which completely removes the risk of a high-pressure steam explosion.
However, the chemical trade-off is severe.
Very severe. Liquid sodium reacts violently, often explosively when exposed to air or water. Every single pipe, pump, and heat exchanger in the plant must be perfectly, flawlessly sealed.
Yeah, the sources mention the 1995 Manju disaster in Japan. A massive liquid sodium leak caused a catastrophic fire and a subsequent institutional cover-up that derailed their entire Fast Breeder Program.
It stands as a stark warning of the rigorous safety culture required to operate this technology.
Considering the engineering nightmare of scaling fission, it is no wonder nuclear fusion gets so much hype as the ultimate clean energy savior.
Oh, definitely.
But the sources highlight a really sobering study from ETH Zurich warning that the economic models currently funneling billions of investment dollars into fusion startups are dangerously over-optimistic.
Right. The ETH study focuses on an economic metric called the experience rate.
Which is what, exactly?
It's the percentage by which a specific technology's cost reliably drops every time its total global manufacturing capacity doubles. Venture capitalists look at green technologies like solar panels and lithium-ion batteries, which enjoy incredibly high experience rates of 8 to 20%.
And they arbitrarily project that fusion reactors will follow that same aggressive downward cost curve once the physics are solved.
Exactly. But a solar panel is essentially a sophisticated Lego brick. Once the design is locked, you can stamp out millions of identical units on an automated assembly line and snap them together anywhere in the world.
A fusion reactor, however, is like a custom-built Swiss watch the size of a football stadium.
That is the perfect distinction. The researchers refer to fusion's onion-like complexity. The systems are so deeply interdependent that if you tweak the magnetic confinement coils in the center, the entire thermal dynamic shifts.
Forcing you to redesign the cryogenic cooling and the structural shielding.
Right. Furthermore, every single plant requires bespoke engineering to accommodate local, seismic risk profiles, specific access to cooling water, and unique national regulatory frameworks.
So mass production is just a fantasy.
The experts conclude fusion's experience rate will likely mirror traditional nuclear fission, hovering around a sluggish 2%.
Okay, let me play devil's advocate here. If fusion requires cracking the physics of a miniature star, navigating an onion-like engineering complexity, and ultimately only yields a 2% cost reduction over time, shouldn't we stop pouring immense climate funds into this sci-fi dream?
It's a tough question.
Wouldn't that capital be better spent deploying the solar, wind, and stage 1 fission tech that actually scales today?
It is a highly pragmatic critique, and the risk of misallocating finite climate capital is exactly what the ETH Zurich researchers are warning against. But the prevailing counterargument from physicists is that the theoretical density and environmental safety of baseload fusion power is so profoundly transformative that society must absorb the research costs, perhaps pivoting towards smaller, modular reactor designs rather than monolithic plants.
Okay, I see that.
However, optimizing our current, highly fragmented global energy grids and supply chains to survive while we wait for fusion requires processing vast amounts of variables simultaneously.
Which is a computational burden that classical Billiken computers are really struggling to shoulder.
Exactly.
So to solve the macro engineering bottlenecks, we basically have to entirely reinvent data processing at the atomic level, exploring quantum mechanics and neuromorphic engineering. Let's look at the quantum breakthrough first.
Sure. A joint team of scientists from Australia and the US recently achieved momentum entanglement using heavy helium atoms.
This is a spectacular confirmation of quantum theory at a larger scale. Historically, we have observed entanglement, where two particles become so deeply linked that they share a single, unified quantum state, mostly in incredibly light, simple particles like photons or electrons.
Right. But by colliding ultra-cold clouds of whole helium atoms, researchers proved that complex, heavy atomic structures can sustain this non-local bond.
Einstein famously derided this as spooky action at a distance, because measuring the momentum of one entangled atom instantaneously dictates the state of its partner, regardless of the physical distance separating them, seemingly bypassing the speed of light.
It's wild. But translating that spooky physics into practical infrastructure hits a massive roadblock called the No-Cloning Theorem.
Yeah, this is a fundamental rule of quantum mechanics stating it is physically impossible to create an exact, independent copy of an unknown quantum state.
Right.
I think of it like a highly classified magic document that instantly incinerates itself the moment you try to slide it into a photocopier.
That's exactly how it acts.
So if you literally cannot copy data, how could a quantum internet or a quantum cloud backup ever function? Because classical internet infrastructure relies entirely on copying data packets across servers and amplifying them through repeaters.
You have identified the central bottleneck of the quantum age. Because the no-cloning theorem, you cannot use traditional signal amplifiers or backup servers.
So what do you do?
If a quantum signal degrades over a fiber optic cable, you can't just copy it and boost it. The information must be securely teleported between nodes or woven through incredibly complex quantum error correction protocols.
Wow.
Engineers aren't just building faster computers, they are being forced to entirely reinvent the fundamental architecture of how information is transmitted and stored without ever duplicating it.
That is wild. And while quantum physicists are battling the laws of uncopyable data, neuromorphic engineers are taking a completely different approach. They're trying to build physical hardware that mimics the low-energy, highly efficient processing architecture of the human brain.
Yes, a team at Cambridge recently published a breakthrough using hafnium oxide films to physically act like biological synapses.
Because the brain processes incredible amounts of data using a fraction of the wattage required by a classical supercomputer, right?
Exactly. Our neurons and synapses process and store information simultaneously, rather than shuttling data back and forth between a separate CPU and memory bank.
And the Cambridge team demonstrated that thin films of hafnium oxide can reliably mimic that synaptic behavior. The commercial significance here is that hafnium oxide isn't an exotic, laboratory-only material.
Not at all. It is already widely used as an insulator in the standard silicon chips powering every laptop and smartphone on the market today.
So the semiconductor industry already knows how to handle the material, but reading the methodology, there's a massive manufacturing hurdle before we see artificial brain chips in our phones.
The fabrication catch.
Yeah.
To create these specific multi-component synaptic films, the material must be processed at temperatures hovering around 700 degrees Celsius.
And that heat profile is fundamentally incompatible with the delicate manufacturing lines currently used to produce commercial silicon wafers, isn't it?
It would completely melt them. They have proven the neuromorphic concept works brilliantly in the lab, but now they must engineer a low-temperature fabrication method to actually integrate it into existing global supply chains.
Man, let's just take a step back and look at the sheer scale of the map we have traversed today. We started by examining how the geopolitical realities of lunar resource extraction are testing the limits of the Outer Space Treaty.
We unpacked the unforgiving thermal physics of dropping a human capsule back through the atmosphere.
And the critical need to enforce preventative licensing and escrow accounts to stop the shotgun blast of Kessler Syndrome in low Earth orbit.
We explored how the desperate need for baseload energy is driving the development of liquid sodium breeder reactors,
while confronting the sobering economic realities of building stadium-sized fusion plants. And finally, we zoomed down to the subatomic hurdles of uncopyable quantum data and brain-like computing.
Seeing how all these disciplines intersect reveals the true architecture of our future. The inflexible laws of physics dictate the boundaries of our engineering.
And that engineering, whether it's an orbital rocket or a fast breeder reactor, creates immense geopolitical leverage.
And that leverage violently disrupts our existing legal and economic frameworks, demanding entirely new paradigms of governance.
For you listening, grasping these intersections provides a massive intellectual and strategic edge. You aren't just memorizing isolated scientific milestones or policy updates, you are seeing the underlying mechanisms that will dictate the next 50 years of global development.
And that development is accelerating blindly. We are building the engine while the vehicle is already in motion.
Which leaves us with a critical question to consider. We've seen how our current international treaties are utterly failing to manage the simple physics of a broken satellite in orbit, and how our institutions struggle to maintain the safety culture required for today's liquid sodium reactors. As we push further, how will our fragile legal and ethical frameworks possibly survive the arrival of unhackable, uncopyable quantum networks and physical hardware that processes information exactly like a human brain?
That is the true test of whether our governance can ever catch up to our genius.
Thanks for taking the deep dive with us. We will see you next time.